Welcome students to the series of lectures of statistics. And in this series of lectures of statistics, we are in the discussion of probability distribution. In the last session, we discussed probability distribution. We introduced probability distribution. And we said probability distribution has two sections. The first section is the discrete probability distribution. The other section is the continuous probability distribution. We also mentioned that in discrete probability distribution, there are three distributions that you have to study in the CFA and FRM curriculum. And broadly, these three probability distributions are Bernoulli distribution, binomial distribution, and Poisson distribution. And today we'll discuss Bernoulli distribution and binomial distribution. Now, what is the reason that we started the discussion of Bernoulli distribution and binomial distribution simultaneously? The reason is very straightforward. These two distributions are similar, or you can also say identical, or you can also say that Bernoulli distribution is the building block of binomial distribution. Okay, and that is the reason we are studying Bernoulli distribution and binomial distribution simultaneously. Now, what is that component which is so identical that we have to discuss both the distribution simultaneously? It is that you cannot use these two distribution until and unless the entity is a dichotomous entity or a dichotomous variable. What is the meaning of dichotomous? Anything which has two outcome. For example, true and false, yes and no, 1 and 0, success or failure. True and false, yes and no, success and failure, whatever variables in this world which has only two possible outcome, then only you can use Bernoulli distribution and binomial distribution. Otherwise, you cannot use Bernoulli distribution and binomial distribution. Okay, so if the entity has only two possible outcome, you'll use Bernoulli and binomial distribution. So if you are interested in knowing whether the stock price will rise or fall, you can use Bernoulli distribution, binomial distribution, right? So think about it, that how we can use Bernoulli or binomial distribution to predict whether the stock price will rise or fall. And by the end of the session, you should be thinking about that. But coming to the basic, Bernoulli distribution can be used for dichotomous variable, but only if you have one trial or one experiment. One trial or one experiment. If you have more than one trial, you should move into binomial distribution, multiple trials. More than one experiment, you should discuss binomial distribution. You should study binomial distribution. Okay. So first, let's study Bernoulli distribution. And to keep everything very simple and straightforward, let's use an entity which has only two possible outcome. And for that, I have chosen toss of a coin. So in toss of a coin, there is only two possibility, head or tail. So you have head, you have tail. And for the time being, in this example, I'm saying my head is my success and tail is my failure. Okay. If you want to flip, it is up to you. Okay. But in this example, I'm saying one thing is success, another is failure. Okay. So head is my success and tail is my failure. Now, this coin, the coin that you're using for the toss, is not a very perfect coin, which has a 50% probability to predict or to get head and tail. It has some flaw, and because of that flaw, the probability of head is what? 60%, and probability of tail is what? 40%. Okay. So if I ask you to plot this in a very simple term, I ask you to plot it. Let's plot it. So you'll plot the outcome on the x-axis, outcome on the x-axis, and probability on the y-axis. And for head, you will write 60%. For tail, you will write 40%. Or instead of head, you can also say success and failure. It is up to you, right? If you plot it in histogram, bar chart, stack chart, whatever way, or even in a table, that is a distribution. That's it. Your 100% probability is being shown distributed between two possible outcome, which is success or failure and head and tail. That is distribution of the probability in the two outcome. And that's why it is called as Bernoulli distribution. What we are studying is the Bernoulli distribution because we are studying something which is dichotomous in nature. The variable is dichotomous in nature. Okay, now this was a very simple distribution, very simple discussion. So Bernoulli is very straightforward and simple. So let's move to binomial distribution, where you will have some of the complexity, but not a lot, because even binomial distribution is considered as the mother of all the distributions. So you don't have to worry about that what kind of a complexity will come in the binomial distribution. That will not come in binomial distribution. Okay. So as you can see that instead of one toss, what I did, I said, okay, let's have five tosses. Toss one, toss two, toss three, toss four, toss five. I have five tosses. Okay, let's toss it. So if you toss the coin, the probability of head is again 60%, and the probability of tail is again 40%. This is one. Now, if I toss the coin first time, second time, third time, fourth time, fifth time, this probability is not changing. So I can say the probability of head occurring or the probability of the success in each tosses, whether the toss is 5 or 100, doesn't matter. Whether you're tossing it for 5 times or 100 times, doesn't matter. Your probability of success and the probability of failure is identical. This is a very critical word. Identical. This is number one. The second thing is there is no influence or relationship between the first toss and the second toss, the first toss and the third toss, the first toss and the fourth toss. There's no relationship. They are independent. And that introduce a very new word in the series of lecture, that is IID. This is the most important word that or the terminology that you learned in the series of lecture. IID, independent and identical variable. What independent stands here for? Independent stands that the first or the second, the third, the fourth, the fifth is not related. They're independent. There's no influence in the outcome of the first to the second to the third to the fourth to the fifth. Independent. The first I stands for independent. The second ID stands for identical. Identical. The probability of the success and the failure is identical in each tosses. Okay? This is very important because binomial distribution doesn't work if this independent and identical IID doesn't hold true. Okay? So it should hold true. Perfect. Okay. So, what is our experiment? Our experiment is very simple. We are tossing the coin for five times. That's it. Now, if I say, what is the probability of zero head in all the tosses? There shouldn't be any head. It should be tail, 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 tail in five tosses. Then, if I ask you the question, what is the probability that if you toss the coin for five times, or you perform this experiment of tossing the coin for five times, there is only one head? What if there is only two head? What is only three heads? What if only four head? What if all the tosses will give you the outcome of head, as in five head? And I want to know the probability. Somehow you got the probability. And what you did, you plotted the possible number of successes. Understand what you plotted on the y-axis, on the x-axis. You plotted the number of successes. And in our example, we have chosen head to be success. You could have chosen it to be failure. It doesn't matter. But we have chosen it to be head. I'm saying, what is the number of successes possible? What is the possibility of zero successes, as in zero head in all the five tosses? One head, one success, two success, three success, four success, five success on the x-axis. And on the y-axis, I have probability. I might have calculated the probability in some way. And if I plotted it, that is my binomial distribution. What distribution? Binomial distribution. So what is binomial distribution? Binomial distribution is the distribution of the probability to the different possibilities of successes. That's it. That is binomial distribution. Okay? Zero successes, what is the probability? One success, what is the probability? Two success, what is the probability? Three success, what is the probability? You plot it or you put it in a tabular format, doesn't matter. That is binomial distribution. Now, the most important thing that you will study today is to find a way, a simple time-saving way to find these probability. These probability are not random. They're coming out of a very simple formula, a simple, very simple formula. That formula is called as probability mass function. What? Probability mass function of binomial distribution. Okay? We'll introduce the formula at the later stage. Why? Because we know how to find the probability with the help of and rule and or rule. We already know that. We don't need that probability mass function formula. So based on the and or rule, that is a rudimentary way to find the probability for binomially distributed entity or dichotomous variable. We can use that formula. But even before using the formula, let's try whether I can or we can find the probability without using probability mass function. And with the help of that method, whatever the rudimentary method will choose, we'll try to find out the probability mass function. So we are doing two things. We are trying to find out the probability of the different outcomes or the different numbers of successes. This is number one. And in doing so, we'll try to derive probability mass function for the binomial distribution. Okay. So let's start with zero successes. Okay. I'm interested in finding the probability of zero successes. As in, what is the probability that head appears zero times in five tosses? Zero times in five tosses. So you toss the coin and you will get tail, 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 and tail. No head. So you are interested in finding the probability of tail in the first, and tail in the second, and tail in the third, and tail in the fourth, and tail in the fifth. The reason I emphasize and because we have to apply which rule? And rule. Perfect. So we have to apply and rule, which is a multiplication rule. But the question is, which formula of and I have to apply? For that, I need to know whether the outcomes are independent or not. And I already mentioned that these are IID outcomes, independent. So we just have to multiply the probability of tail, 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 tail in each tosses. What is the probability of tail? 0.4. Let's multiply. 0.4 into 0.4 into 0.4 into 0.4 into 0.4, which is 0.4 raised to the power 5, and that is the probability. So if you're interested in finding zero heads or zero successes in your five tosses, that is 0.4 raised to the power 5. Very simple, straightforward. Perfect. But what if I tweak the question and say, if you toss the coin five times, I'm interested in head appearing only one time. Now, this makes the question slightly complex because there are different combination possible. What are those combination? The head can appear in the first toss, the head can appear in the second toss, the head can appear in the third toss, the head can appear in the fourth toss, and head can appear in the fifth toss. This can happen, or this can happen, or this can happen, or this can happen, or this can happen. So you have to apply OR rule. OR rule is for what? Addition. So you have to add. Okay, perfect. And important, if this will happen, then this won't happen because they are mutually exclusive. So probability of A plus probability of B minus nothing, right? So you have to add the probability. But even there, you have to find the probability of this one combination. What is the probability of this happening? That head will appear in the first, and second, third, fourth, and fifth will have tail. It is 0.6 because that is the probability of head, into 0.4 because it is and, into 0.4 into 0.4 into 0.4. What about this? It should be 0.4 for the tail, then 0.6 for the head, into 0.4 for the tails. Now, in each one of them, if you write it, you will always get 0.6 raised to the power 1 into 0.4 raised to the power 4. Let's try for the last one. Even for the last one, you will write 0.6 in, sorry, 0.4 into 0.4 into 0.4 into 0.4 for 4 tails. and then 0.6. So again, it will give you 0.6 raised to the power 1 into 0.4 raised to the power 4. And you have to add how many times? 1, 2, 3, 4, 5 because of the OR rule. So at the final, when you add it for 5 times, it would be 5 into 0.6 raised to the power 1 into 0.4 raised to the power 4, right? Now I'm introducing a formula for you. What are you doing actually? How you got this 5? You got the 5 by writing all the possible combination. But in mathematics, you already have that formula. That is 5C1. 5 is the total number of trial. 1 is your interested success, which is only one head. 5C1. You will get the number 5. What is this? This is the probability of what? Head or probability of success? You are interested in only one success, so I'm writing it as X. Instead of 1, I'm changing the notation and saying X stands for the number of successes. Okay? And P stands for the probability of success. Okay. What about 4? 4 is the probability of failure. Let's write it as Q. Q, probability of failure. And N minus X, 5 minus 1. What 5 stands for? 5 is the total number of trial, and I'll convert it to N. So the formula that I'm writing is NCX, P to the power X, Q to the power N minus X. That's it. Either you apply a rudimentary method to find the probability, but it is very time consuming. Understand, you have to write all the combinations. Then you write all the possible probability. Then you sum it up. It is a time consuming exercise. Instead of that, you can simply use the formula. I have derived the formula from this rudimentary method only. I haven't done anything fancy here. This is the probability mass function for binomial distribution. What is probability mass function? Probability mass function is a function which throws probability. What it does, probability mass function is a function which gives you probability as an outcome if you provide your interested X, which is the number of successes in the case of binomial distribution. If you're interested in 0 success, just put down in the formula. If you're interested in 1 success, just put down into the formula. If you're interested in 3 success, just put down into the formula. Let's test it. Let's test it. Okay, so I'm going to test it for, say, 2 tosses. Okay, so head appearing, sorry, I'm testing it for head appearing 2 times in 5 tosses. Okay, so the experiment remains the same. I'm tossing the coin for 5 times. I'm interested in head appearing 2 times. So you see head appearing here in the first and the second, or it can occur in a sequence where head occur in the first toss and the third, or it will occur in the first and the fourth, first and the fifth, second and the third, second and the fourth, second and the fifth, third and fourth, third and fifth, fourth and fifth. What are the total number of outcomes possible? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you'll first write 10 into, then you'll try to find out the probability of any one of the combination possible. You will write 0.6 raised to the power 2 into 0.4 raised to the power 3. Now, if you just apply this formula, NCX, P to the power X, Q to the power N minus X, you don't have to worry about the combination because it is already in the formula. You have to write the total number of trial. What is the total number of trial? 5. Combination. What is the total number of successes you're interested in? X, that is 2. What is the probability of success? 0.6. What is the total number of successes you're interested in? 2. What is the probability of failure, which is tail? 0.4. What is N? And is the total number of trial. What is X? The number of successes you're interested in. 5C2 is what? 5 factorial upon 2 factorial into 5 minus 2, that is 3 factorial, into 0.6 raised to the power 2, 0.4 raised to the power 3. Okay. If you break it, then at the end, you will get it. The answer that you will get is 10 into 0.6 raised to the power 2 into 0.4 raised to the power 3. Final. And that is the probability mass function. NCX, p to the bar x, q to the bar n minus x. And that is the probability mass function which was written on your slide in the previous slide as well. NCX, p to the power x, q to the power n minus x. There are different ways to write it, but uh, the intuition is same, that you write the combination possible, you write the probability of success, write the probability of failure, and you decide what should be the power of the probability of success and the probability of failure. That's it. And with the help of this formula, we got the different probabilities, right? With the help of this formula, we got that what is the probability of 0 successes, 1 successes, 2, 3, 4, and 5. These are the probability. Okay. Now, there are three important things that you have to understand in the binomial and Bernoulli distribution. The first was the probability mass function. The second is the mean, and the third is variance or standard deviation. Okay. But I'll pause here because I want you to first digest this probability mass function. I want you to use this probability mass function to predict whether the stock price will rise or fall. And once you are comfortable with the probability mass function, we'll enter into deriving mean and variance for binomial distribution. See, I can give you simply the formula that, okay, the mean formula is n into p. N is the number of trial and p is the probability of success. That's it. Take the formula, go home. Probability, take the formula, go home. And for variance, it is NPQ, where n is the number of trial, p is the probability of success, and q is the probability for failure. I can just give you the formula and story ends. You can just remember the formula here. But in the next session, we'll try to derive this formula. This formula of mean is not just n into p randomly coming out of some intuition. It is derived from something. So we try to find out from where you got this n into p, from where you got n into p into q. I just want to give that intuition to you. It's not important whether I will write the complete derivation, but it is important that you get how to derive and reach to n into p. Okay. With that, I'll pause here and see you in the next session. Thank you. Have a nice day.